In the previous video, we saw how to represent curves with parametric equations. In this video, we will learn how to work with this concept in the context of calculus. Please don't forget to click to the like button, subscribe to our channel and activate the notification bell. Your support is crucial for our channel's growth and enables us to continue creating quality content. Thank you in advance for your support. As I said a few moments ago, we saw how to represent curves using parametric equations. Now we'll apply calculus methods to these parametric curves. In particular, we'll solve problems involving tangents, areas, arc lengths, and surface areas. You've probably already learned derivatives of parametric equations using the chain rule. But if you are more interested in the fundamentals of calculus, you want to understand how to prove the derivative of a parametric function using limits. Let us consider a function in which the coordinates x and y are given in terms of a parameter t. That is, we have x equals f of t and y equals g of t. For parametric functions, we can express delta y and delta x in terms of delta t. When t varies to t plus delta t, the coordinates x and y vary to x plus delta x and y plus delta y, respectively. Therefore, we can rewrite delta x and delta y as follows. First, note that the quotient delta y divided by delta x represents the slope of the second line determined by points P and Q. The limit of this quotient as delta x approaches 0 gives us the slope of the tangent line at P and consequently the slope of the curve. We know that the definition of the derivative of a function f of x is the limit as delta x approaches 0. Since small changes in x correspond to small changes in t, then delta x approaches 0 implies that delta t approaches 0 as well. We can divide the numerator and denominator by delta t and rewrite the derivative as follows. By the property of limits, if the limits of the numerator and denominator exist, we can write, recognizing the terms in the numerator and denominator as the definitions of the derivatives of g of t and f of t with respect to t respectively, we arrive at the formula for the derivative of a parametric function. Let us proceed by stating the following theorem, which has just been demonstrated. Let c of t be a curve parameterized by the differentiable functions x equals x of t and y equals y of t. Assume that dx dt is continuous and non-zero. Then the derivative dy dx is given by. Let's now solve some problems involving tangents. Find an equation of the tangent to the parametric curve x equals t minus 3 times sine of t and y equals 4 minus 3 times cosine of t at the point t equals 4.5. Find the points on the curve where the tangent is horizontal or vertical. The figure below shows the graph of the parametric function in its respective domain. The first step is to find the derivative for each of the parametric equations, and then find the slope at t equals 4.5. The next step is to find the coordinates of the point for which t equals 4.5. We can determine the corresponding xy coordinates by plugging this value into the parametric equations. Next, we will write the familiar tangent line equation and substitute the other pair we just found into it to determine the required tangent line. To solve part B, we first need to discuss the problem of finding the horizontal and vertical tangents of parametrically given curves. Briefly, we need to find the critical points of the curve, and this is achieved by setting the derivative equal to 0. On parametrized curves, there are two types of critical points: points where the tangent line is horizontal and points with a vertical tangent line. Horizontal tangents will occur where the derivative is 0, and that means that we'll get horizontal tangents at values of t for which we have dy dt is 0 and dx dt is non-zero. Vertical tangents will occur where the derivative is not defined, and so we'll get vertical tangents at values for t for which we have dy dt is non-zero and dx dt is 0. To find the points where the curve has a horizontal tangent, we need to set dy dt equal to 0 while ensuring that dx dt is not equal to 0. Setting dy dt equals 0 gives us the equation 3 times sine of t equals 0, or sine of t equals 0. This equation has 4 solutions in the range from 0 to 10. T equals 0, t equals pi, t equals 2 pi, and t equals 3 times pi. For these values of t, we can verify that dx dt is indeed non-zero. Now that we have found the values of t that yield horizontal tangents, we can determine the corresponding x, y coordinates by plugging these values into the parametric equations. Therefore, the horizontal tangents will occur at the following points. To find the points where the curve has a vertical tangent, we set dy dt to be non-zero and dx dt to be 0. Setting dx dt equals 0, we obtain the equation 1 minus 3 times cosine of t equals 0, which simplifies to cosine of t equals 1/3. You should use a calculator to find the angle whose cosine is 1/3. Solving this value, we obtain 1.23. This value is in the range 0 to 10. Be careful now, because we must find other solutions using the periodicity of the cosine. The cosine function has a period of 2 times pi, and general solutions to cosine of t equals 1/3 are given by t equal 2 plus or minus 1.23 plus 2 pi times k, where k is an integer. The plus or minus sign is crucial, since the cosine function is even. Cosine of t equals cosine of minus t. There are two solutions for each value of t. Replacing k with 0, 1, and 2 in both cases and examining the solutions, we should eliminate the solutions that are outside the interval. We can see that we have only 3 solutions. Now that we have found the values of t that yield vertical tangents, we can determine their corresponding xy coordinates by plugging these values into the parametric equations. Therefore, the vertical tangents will occur at the following points. Let's calculate arc length using parametric equations. This topic is a clear application of the definite integral. The arc length of a curve defined by y equals f of x from x equals a to x equals b is obtained through a definite integral. Now let's explore arc lengths using parametric equations. If a curve is described by x equals f of t and y equals g of t in the interval from alpha to beta, and it traces the curve exactly once from left to right where dx dt is greater than 0, we can derive the arc length formula for parametric equations. Follow along with the substitutions and algebraic manipulation. After all this, we can say that let C of t be a curve parametrized by the differentiable functions x equals x of t and y equals y of t. Assume that dx dt is continuous and dx dt is greater than 0. Then the arc length L for alpha to beta is given by. Let's see how it works. Graph each of the following curves and find its length in the given interval. To find the arc length of a parametric curve, we integrate the square root of the sum of the squares of the derivatives of the parametric equations with respect to the parameter. Let's solve part A. First, compute the derivatives of the parametric equations with respect to the parameter t, dx dt and dy dt. Next, square both derivatives, sum them, and then take the square root of the sum. Finally, integrate the result over the specified interval. This integral represents the total arc length of the curve within that parameter range. Since this integral does not have an elementary antiderivative, it requires numerical integration. Let's solve part B. To calculate dx dt and dy dt, we will use the product rule as both functions are products of two other functions. The derivative of the natural exponential function is itself, while the derivative of cosine is negative sine, and the derivative of sine is cosine. Next, we sum the squares of the derivatives of the parametric functions and simplify the expression to prepare for integration. Fortunately, this integral is much easier to solve. Now let's find a formula to determine the area under a parametric curve given by the parametric equations. The graph below shows a parametric curve C with equations x equals f of t and y equals g of t over an interval from a to b. First, let's review how to find the area under the curve y equals f of x. Now we'll take the derivative of x. Substituting these results into the area formula yields the area under a parametric curve. Let C be a curve parametrized by the differentiable functions x equals f of t and y equals g of t on a to b. Let us also assume that C has no points below the x-axis and is transversely from left to right as t increases from A to B. The area under C is given by. Let us see how it works. Find the area bounded by parametric equations. First, calculate the derivative of x with respect to t, and then plug the result into the formula to calculate the area. Apply it to the area formula. Expand the integrand and integrate term by term. Parametric curves can be rotated around multiple axes to generate surfaces of revolution. Now we will determine the surface area of a region obtained by rotating parametric curve around either the x-axis or the y-axis. The surface area of a surface of revolution is found by integrating the product of the circumference of a circle formed by rotating a point on the curve and the arc length element along the curve. The formulas differ slightly based on whether the curve rotates around the x-axis or the y-axis. Likewise, we can adapt these two surface area formulas for parametric equations. To find the surface area in this case, we simply need to modify the expression for ds. If a smooth curve x equals f of t, y equals g of t on A to B is transversely exactly once as t increases from A to B, then the areas of the surface generated by revolving the curve about the coordinate axis are as follows. Let us see how it works. Find the area of the surface generated by rotating the curve about the x-axis. Find the derivatives dx dt and dy dt. Next, find the differential element of the arc length ds. Substituting this into the surface area formula, we obtain Next, to calculate the integral, we will perform the substitution t equals tangent of u, and the derivative of the tangent is the secant squared. We also need to change the limits of integration. When t equals 0, u equals 0. And when t equals 1, u equals pi over 4. The square of the secant of an angle is equal to 1 plus the square of the tangent of the same angle. We can express tangent to the fourth power in terms of secant of u. We will solve the expression in separate integrals to facilitate the calculation of each known integral. The integral of secant cubed of x can be solved using integration by parts. I choose z equals secant of u and v equals tangent of u because the derivative of secant is the product of secant and tangent, while the derivative of tangent is the square of secant. Furthermore, the integral of secant is given by the natural logarithm of the sum of tangent and secant. After some algebraic manipulation, we obtain the integral of secant cubed. The integral of secant to 5 can be solved using integration by parts, similar to how we solved the integral of secant cubed. Now we will define z equals secant cubed and v equals tangent. Follow along step by step. The integral of secant to 7 can be solved using integration by part, similar to how we solved the integral of secant to 5. Now we will define z equals secant to 5 and v equals tangent. Follow along step by step. Finally, we substitute the results of the integrals and calculate the surface area. Now let's move on to the final topic of this video. Let's take a look at finding the second derivative of y with respect to x. Calculating the second derivative is important if you want to determine where a curve concaves upward and downward. To calculate the second derivative, we use the formula for the first derivative twice. To calculate the second derivative, first solve for dy dx, then differentiate y prime with respect to t and plug it into the formula to calculate the second derivative. Let us see how it works. Determine the values of t for which the parametric curve given by the following set of parametric equations is concave up and concave down. To determine the concavity of the parametric curve, we need to calculate the second derivative of y with respect to x. First, we will find dx dt and y dt. Next, we will compute the first derivative of y with respect to x. Finally, we will use this result to calculate the second derivative. The second derivative will only be 0 at t equals 0. If t is greater than 0, the second derivative is greater than 0 as well. Then the function is concave upwards. If t is less than 0, the second derivative is less than 0 as well. Then the function concaves downward. The graph provides a clearer illustration of how to solve this problem.